Hello everybody, hope you are doing well. This presentation belongs to the part of the course System Control and Automation, focusing on Proportional Integral Derivative Controller, PID Controller. First, I will explain what is a control system and the different types of control system that we have, the main components of the control system, then focusing on controllers and PID controller in particular. So let's get started. What is a control system? As you see in the single black diagram here, a control system is a system that can provide the desired response by controlling the output. Actually, the output is controlled by varying the input. I'll explain you how to vary this input in order to get desired response in next slides. Okay, we have a lot of control system in our daily life. One of them could be traffic lights control system. As you see here, a sequence of input signal is applied to this control system, and the output is one of the three lights that will be on for some duration of time. During this time, the two other lights will be off. Based on the traffic information, for example, at a particular junction, the off or on times of the lights can be identified. I'll show you more examples for control system in next slides when we are going to talk about the different types of control system later. Okay. We have both manual and automatic control system. For example, we want to control the water temperature. Here in manual control system, you see to keep a constant temperature of water discharged from an industrial gas fire heater. An operator has to watch a temperature gauge and adjust a fuel gas valve accordingly. If the water gets too cold, he has to open the gas valve. If the water temperature becomes too high, the operator has to close the gas valve, just enough to bring the temperature back to the desired value. I know you are thinking about the drawbacks of this manual system. So let's see what are the drawbacks here. As you probably know, the manually process is very time consuming, and there might be the mistakes brought by personal operation errors. You know, the operator might be tired, sleepy, distracted, so there are some errors here. It is a dangerous working environment for operator, as a potential catastrophic situation might occur. And the manual control cannot achieve a good accuracy and stability. So this is the time to use an automatic control system instead of humans in many laborious operations or dangerous working environment. So to make this system automatic, here we need some things. We need to install an electronic a temperature measurement device like transmitter. We need to automate the valve by adding an actuator so it can be driven electrically without human interactions. And we need to install a controller that it can be a PID controller and connect it to the temperature measurement device, here the transmitter, an automated control valve. The main actually part of the control system is the controller, that we will talk about that. Let's see how this control system works. The operator sets the controller's set point or SP to the desired temperature, and the controller's output, here CO, sets the positions of the control valve. The temperature measurement, the transmitter here, called the process variable or PV, is then transmitted to a controller like PID controller, which compares it to a set point and calculates a difference or an error, which call it E, between these two signals, the set point, the desired values, and the process variable. Based on the error, the controller's tuning constants, the controller can calculate the appropriate controller output to set the control valve at the correct position to keep the temperature at a set point. Okay. Let's see, we have different types of control system. We have continuous time control system that you can see the block diagram here. All the signals or functions are continuous time t. We have a discrete time control system that here there exists one or more discrete time signals. We also have SISO, single input and single output control system. As you can see here, we have only one input and one output. And we have also MIMO, or multiple input and multiple output control systems. As you see, we have multiple inputs and multiple outputs. Finally, we have open loop control system and closed loop control system that I'll show you in next slides. The open loop control system, which referred to as a non-feedback control system, is a type of continuous control system in which the output, as you see here, has no influence or effect on the control action of the input signal. So you see, it is a very simple system, and we don't need many maintenance. The operation can be done very quickly, and it's so cost effective. There are a lot of examples for open loop control systems that here we want to consider clothes dryer, which use in our daily life. The clothes dryer whose control action is done manually by the operator. Consider this one. Depending on the wetness of the clothes, the dryer has to stop accordingly, but in case of manual operation, the operator sets a time, for example, 15 minutes. The dryer will stop at 15 minutes. Even the clothes are wet. This is because we don't have any feedback here. And there are some disadvantages. Actually, the open loop control system works perfectly when there is no unexpected events or input variations. There are other examples of open loop system like a traffic light, TV remote, hair dryer, washing machine, and so forth. The other type of system is closed loop control system, or which is known as feedback control system. And here the output has an effect on the input, as you see, which is called closed loop system. In this system, if an error has occurred in the output, then it is compared to the reference signal or set point, and the error is corrected in each single time. So the system would be high efficiency. This system is so accurate, reliable, and works very well in unexpected environment and input variations. But as you see, as we have a lot of components here, it would be very costly and expensive, and when there is a high maintenance. Let's see an example in real life. Again, I like to refer to clothes dryer as an example for the feedback control system, because we have already had this example for open loop. So let's see the difference. The clothes dryer control action here is done automatically. Depending on the wetness of the cloth, the dryer has to stop accordingly. Even if the operator says the time like 15 minutes, the dryer will not stop until the clothes are completely wet. Even it takes more than or less than 15 minutes, because here we have a feedback loop, and this feedback loop always sends the wetness of the cloth by a sensor, and it sends the signal to the controller here and compare each time with the reference value or desired value, and stops the dryer when the cloths are dried completely. There are examples of closed loop control system like electric, iron, air conditioners, temperature control systems, and so forth. Let's see what are the components of a control system. As you see, sensors that are used to measure the system variables. We have the controller that calculates the error, the difference between set points and feedback signal. We have actuator because the controller cannot connect directly to the process and plant. So this actuator is used to manipulate the variables. We have the disturbance, process, and the set points or reference input that are predefined values by operator that we are trying to get this desired value in our control system. We have also functions that I'll show you in next slides. Okay, what is a PID controller? As you see, PID controller is an instrument that are used in industrial applications to control and regulate, the flow, pressure, temperature, speed, and other process. Here I'd like to tell you a brief story of PID controller. The first evaluation of the PID controller was developed in 1911 by Elmer Spree. A few years later, in 1933, Taylor Instrumental Company, Tech, introduced the first pneumatic controller with a fully tunable proportional controller. And in 1940, Tech developed the first PID pneumatic controller with a derivative action, which reduced the overshooting issues. And in 1942, two people introduced tuning rules, and after that, in 1950, the first automatic PID controller was widely adopted for industrial usage. Here we have the main structure and actually the terminology of the PID controller. PID controller, as you see, is a control loop feedback mechanism that is widely used in industrial control systems. A PID controller calculates the error value at difference between a measured process variable and desired set point. The controller tries to minimize the error by adjusting the process through the use of manipulated variables. Here we have three control terms: the proportional or P, the integral or I, and derivative or D here. Actually, the proportional or P depends on the present error, and here the integral or I is actually depending on the accumulation of the past errors, and this one, the derivative or D, is a prediction of future errors based on the errors that we have. And finally, the weighted sum of these three actions are used to adjust the process via control elements. Here the terminology, I've already talked about error, proportional, integral, derivative. Here we have p factor or kp, which is a constant value to increase or decrease the impact of proportional. And ki and kd are also constants value to increase or decrease the impact of integral and the impact of derivative here. PID controllers have three control modes: the proportional control mode, integral control mode, and derivative control mode. You see a large value of Ti result in a slow integral action, and a small value of Ti here result in a fast integral action. If the integral time Ti is set too long, the controller will be sluggish. If it is set too short, the controller loop will fluctuate and become unstable. In this figure, the TS here is the control algorithm's execution interval. That sometimes it's called like sampling time or scan time. Finally, here we have derivative control mode or future error. For a given error here, as you see, the derivative control mode produce an output based on the change of the error here. A derivative mode is sometimes called rate, and the derivative mode produces more control action if the error changes are fast. And if there is no changes in error, like here, the derivative action will be 0. The derivative mode has an adjustable setting called derivative time or TD. The larger TD setting, the more derivative action is produced. A derivative time setting of 0 effectively turns off this mode. If the derivative time is set too long, there will be some fluctuation, and control loop will run unstable. Here we have the equation. As you see, the derivative is equal to the controller gain Kc multiplied by derivative time over Ts multiplied by the difference between previous error and the current error. The final expression and PID flowchart in this slide. The PID controller scheme is named after its three correcting terms: the proportional, integral, and derivative. And that we can call it UT, the output signal, or MV, the manipulated variable. As you see, it is the sum of these three terms: the proportional, the integral, and the derivative terms. And here are the definition of each parameter: Kp, Ki, Kd, the error and time, and this is the tau here. Here we have the algorithms or forms of a controller. Manufacturers of PID controllers arrange the proportional, integral, and derivative modes into one of the three control algorithms or forms that you can see here. They called parallel, standard or non-derivative, and derivative. So let's see each of these forms. The parallel form, as you see here, the set points the desired value. For example, the temperature of the heater fed into the system, and this the process variable and these set points are compared and the error is achieved. This error fed into the controller, the PID controller here, and you see this PID controller consists the three terms, the proportional, integral, and derivative in parallel. So the output of this controller is some of these three terms. We need to have the transfer function GCS, which is the sum of these three transfer function. You see, for the first one, for the proportional term, the transfer function is Kp. For the second one, the integral one, is Ki over S. And for the third one, for derivative, is Kd multiplied by S. You see, the Kp is proportional gain, Ki is integral gain, and Kd is derivative gain. We have the standard form. As you see, this is the controller, the PID controller, and you see this KSC or control gain impacts the other terms, the proportional, integral, and derivative. And we need to calculate the transfer function here for PID controller. Before that, let's see. We know that Kc is control gain, and we have Ti here, which means the integral time that we have already had, and TD, which is derivative time. So the transfer function of this standard form is Kc multiplied by the transfer function of this one, which is 1, plus the transfer function of this part, which is 1 over Ti multiplied by S, plus the transfer function of the derivative terms, which is Td multiplied by S. The next one is interactive form. As you see, the PID controller consists this part. There are we have this sequence here, and the transfer function here is Kc multiplied by the transfer function of this block, which is 1 plus 1 over Ti multiplied by S, and here multiplied by the third transfer function, which is 1 plus Td multiplied by S. As you probably know, Kc here is controller gain, and Ti is integral time, Td is derivative time. You see the Kc here interact the other terms here. So that's why they call it interactive form. Okay, here we have the controllers. We can have only proportional controller. We can have proportional with integral controller, and proportional, integral, derivative controller that we call it PID. Let's see each of these controller. The proportional or P controller, as you see here, the proportional gain is not 0, but the integral gain and derivative gain are 0. And here the Kc or controller gain is equal to proportional gain. The controller output or output signal can be calculated as Kc, which is the controller gain multiplied by an error, which is the difference between set points and the process variable, plus a bias. For industrial processes, that most of them are nonlinear, we need to convert this nonlinear system to the linear one and do linearization, because PID controller just work with linear system. To do so, a signal bias is needed to add to our equation here. Next, we have a proportional integral or PI controller. As you see here, we have the controller gain and the proportional and integral terms here. So the output signal or controller output is equal to the controller gain multiplied by error plus the terms, the integral terms here. And last one is proportional integral derivative or PID controller. As you see, it includes all the terms proportional, integral, and derivative. So the controller output here can be calculated as a the controller gain multiplied by the error multiplied by these terms here. This figure shows the difference between P controller, PI, and PID controllers, and actually when we don't use any controller. As you see, the error is very high when we don't use any regulation terms, any controllers. When we use a P controller using proportional term, that you see this curve here, there is a small error. To reduce this error, we add the integral term to the proportional term and create the PI controller. The response time for PI controller, as you see here, is 0 after, for example, TS seconds. So the output is equal to the set points after some seconds here. But by integrating P and PI controller, we can see we have some fluctuations here. So to overcome this issue, we can add the derivative term to the proportional and integral and actually create the PID controller and see the response time for that. And you see this response time, and which is 0 after a few seconds, and there is no fluctuations here. And actually the fluctuations refuses. This slide shows the effects of varying PID parameters Kp, Ki, and Kd. As you see, these parameters are changing, and finally you see the step response of a system here by varying these parameters. Okay, let's discuss about proportional gain. You see this figure shows the response time due to the different proportional gain. For example, this blue line here shows the response time when Kc is 1, and the orange one is for when the proportional gain is 2. This yellow one shows the response time when the proportional gain is 4, and this is the reference value or desired value that you see. There is a smaller error between the response time when we have Kc equal to 4. For integral gain, we have the same, for integral time, when the integral time is equal to 4, you see these blue curves here and these fluctuations that are, considerable. Then it shows the response time for when we have Ti equal to 12, this yellow curve here, and you see the reference is shown in purple here. Based on these values, you see the orange one when ti is equal to 8 is better than other lines. We have here the derivative gain as well for different values of td or derivative time, and you see the results. The result for td equal to 1 is better than other values. Here is the effect of performance. You can see the table here and the references that I've used for this presentation. Hope you enjoy this video.